In part D, we're going to look at the concavity and the inflection points of big F, which will require a slightly different approach than we took in parts B and C. You'll notice as I highlight the phrases concave up, concave down, and inflection points, I'm using a different color highlighter than I did in parts B and C, and that's to harken back to something I did in part A that deliberately is meant to attract your attention to one specific color-coded fact. The concavity and inflection points are related to the second derivative of a function, and I highlighted a fact that we established in part A about the second derivative, namely that big F double prime, the second derivative, is little f single prime. So when I want to understand information about concave up, concave down, and inflection points, I know that big F isn't going to cut it. Big F doesn't give me the information that I need, but little f does. So making that connection in part A was actually super helpful because it's going to allow me to do this question as well. Just to recap some of the phrases here before we jump into the calculus, big F is concave up if big F double prime is positive. You'll notice I took similar notes when I was doing the video for part B, so I'm just going to keep this little note-taking thing going in case you need it. If big F is concave down, it's because its second derivative is negative. So we know those facts because those are straight function analysis facts. We've seen those facts before. Big F is concave up when its second derivative is positive. Big F is concave down when its second derivative is negative. And that's great when we know information about big F, but we don't. The loophole that we're using here is that we don't know enough about big F to say anything decisive, but we do know little f. So I'm going to make a substitution in this little fact. Instead of where it says big F double prime, because I don't know what big F double prime is, I'm going to replace that with little f single prime. Because again, that was a key fact that we already established. Big F double prime is the same as or equal to little f single prime. So I'm going to replace in my little notes here big F double prime with little f single prime. Little f single prime must be positive when we're talking about concave up. And little f single prime must be negative when we're talking about concave down. So that feels like information I can find. Little f is stuff we can do. Remember how we talked about that in part A? Little f prime is just a slope. And I can find a slope of little f. I can just look at the graph and find the slope of little f. And if I need to know where a slope is positive or negative, I can definitely do that visually. So I'm just going to make those little notes to myself. I'm really just going to look at the graph and see where the slope of little f is positive. That'll tell me concave up. And I'll look at where the slope of little f is negative. That'll tell me concave down. That'll tell me all the information I need, just in kind of a roundabout way. It's not going to tell me directly about big F, the way the question is phrased, but it's going to give me all the info I need as long as I know what to look for. Now, always with concavity and inflection points, we rely on a line chart. So I'm once again going to draw myself a line chart, figuring that we're going to do and analyze big F double prime, but my labeling suggests that since that's not what I'm really looking at, I'm going to also label it little f single prime, because that's what I'm actually going to look for. I'm actually just going to be looking for slopes. So you'll notice I'm trying to write all the things here so that way we can see where this info is coming from. I'm just going to look at the slopes of the graph of little f, and that's going to dictate my whole line chart. Always with the line chart, if you have boundaries, put those on the line chart before you start. So I'm going to start with the boundaries at -4 and 6. Now, I'm going to think about what I always need for a line chart. Zeros, pluses, minuses. I'll start with zeros. Now, zeros, in the context of slope, are anywhere that the slope itself on the graph is 0. I should also make the important distinction that we should also be looking for slopes of undefined, sharp points, because those are also classified as crucial or critical points. They could also be inflection points. So I don't just want to look for slopes of 0. I do want to look for undefined values as well. So I'm going to look at my graph, and I'm going to look for wherever the slope is 0 or undefined first. Now I just usually go from left to right. The first undefined slope that I see is right here because of a sharp point on the graph. So it looks like at -3, I have a sharp point, so I'll put 0 with a slash through it like so. That's my symbol for undefined. Then I'm going to go back to my graph. It looks like I have another sharp point over here at x-coordinate -2. So again, I'll put a sharp point on my line chart to compensate. Then it looks like I have another sharp point here at 0. So again, I'll record that with an undefined symbol. At 2 on my graph, it looks like I have a flat or a horizontal slope. So that horizontal slope would be a value of 0. So at 2, I'll show the slope has 0. Then I'm looking back, it looks like I have another sharp point at 4. So I'll do another undefined at 4. And then of course it just ends, so I'm not going to worry about that. So in terms of zeros and critical values, I know where the slope has a 0 or an undefined. That was step 1. Next step is the pluses and the minuses. So I'm going to look back at my graph in these little subintervals, and I'm going to look at the nature of the slopes of the graph. So between -4 and -3, I'm looking at the slope. I'm seeing all of this as one big negatively sloping piece, so I'll put a minus sign to show that the slope of the graph is negative in that section. Now I'm going to look between -3 and -2. Between -3 and -2, that whole segment is positively sloping, so I'll put a plus sign there. Between -2 and 0, actually I kind of missed something. It looks like I had another sharp point that I missed at -1. And the reason why I needed to squeeze that in there, and if you noticed that and were yelling at your screen because you were like, Herbert, you missed a sharp point. Sorry about that. Between -2 and -1, the slope just looks like it's 0. So I'm going to squeeze a little 0 in between to show that it's all flat in there. Between -1 and 0, it looks like I have a negative slope, so I'll squeeze a minus sign in there. Sometimes these line charts get really messy, so the bigger you can make it, the better. Between 0 and 2, all of those slopes look like they'd be positive because they'd be sloping upwards, so that would be a positive slope there. Between 2 and 4, that would all be negatively sloping. And between 4 and 6, we're still negatively sloping. So the line chart is jam-packed with information, but we know we figured out all the important info we need. We needed all the pluses because that's telling us where we have concave up. We needed all the minuses to tell us where we have concave down. And we needed to be able to see where we switch from plus to minus so that we can see possible inflection points. So let's break this down. Big F will be concave up in the following subintervals where big F double prime is positive. So I'm looking at my line chart, looking for pluses. I see one here between -3 and -2. I see another plus between 0 and 2. So it seems as though, based on my line chart, the intervals on which I'm concave up are -3 to -2 in union with 0 to 2. So that looks pretty good, and that follows the logic I've always known, that big F is concave up when its second derivative is positive. By the same logic, I can predict where big F is concave down. We are concave down wherever our line chart shows negatives. So I see those between -4 and -3. I see another little negative tucked in here between -1 and 0. Another section from 2 to 4, and another section from 4 to 6. So that's kind of a lot. So concave down, I'll have quite a list of options here for -4 to -3, in union with -1 to 0, in union with 2 to 4, in union with 4 to 6. Some people argue that you can lump 2 to 6 all together into one single interval. That's fine if you do. It's fine if you don't. It doesn't really matter. It's just kind of a personal preference thing. If you don't feel like you understand the nuances of when you're allowed to versus when you're not allowed to lump things together into single intervals, then just don't and write them all separately, because there's nothing wrong with that. That's the safer of your options. Now, let's talk inflection points. Big F has inflection points at any x coordinate where the sign of big F double prime changes from negative to positive or from positive to negative, where the sign truly changes. Changing from 0 to something doesn't actually necessitate an inflection point. So I'm going to look only for where we go truly from positive to negative. And it looks like that happens here at -3, because you can tell at -3 we had a negative, then a plus. So the concavity switched, therefore we definitely have an inflection point there at x equals -3. Now I look here at -2 and I don't see an inflection point because I have a plus to a 0. That's not a true change in sign. Same thing with -1. We change from 0 to negative, but that's not a true inflection point. At 0, though, we do have something good happening, because at 0, we switch from negative to positive. That's a full switch in concavity, so that means x equals 0 is another inflection point. And then if I keep looking, I see one more here at 2, because again, I see a full change in inflection. I see a full change from positive to negative. That's a full change in concavity, so x equals 2 must be my last inflection point. 4 doesn't count because the concavity was down, or negative, didn't change, so it just stays concave down the whole time, therefore no inflection. So all of the things that we know about concavity and inflection points are still true, namely that it's all based on the second derivative. Concave up, second derivative positive, concave down, second derivative negative, inflection points where concavity changes from positive to negative, and all of those things that we just found came from a loophole in the setup of the problem. We never actually directly analyzed big F, even though all of our answers are about big F. We analyzed little f. And that was our second fundamental theorem loophole. Little f told us what we needed in order to get all of these answers, even though the answers themselves are about big F. It's kind of tricky, it's kind of weird, it's just something to keep in mind. Now, in the last example, we're going to talk about what big F should look like. So make sure that you understand now what all of our answers from B, C, and D are really telling us about big F. What is increasing and decreasing telling us about its shape? What do its min and max tell us about those peaks, highs, and lows, if you will? And what does its concavity tell us? How can that help us picture what big F will look like? Because all of our observations are going to help us in letter E to sketch a function that we can guess represents big F, even though we've never actually seen it. So think about what all your answers up to this point mean, and in letter E we'll tie it all together.